Hello, I'm Michael Ekstrand, the lead developer of LensKit and a PhD candidate in computer science at the University of Minnesota with the Group Lens Research Group. This video explains some of the organization and design of LensKit to give you an overview of what the various classes are, how the source code is laid out, and how to go about starting to use LensKit. In this video, I'll talk a bit about the project's goals, why did we create LensKit and what role do we want it to serve, the core APIs for using LensKit to provide recommendation services, the layout of the various LensKit modules, what's where, what to depend on, etc., and then the architecture of how a LensKit recommender is built, along with a walkthrough of the Hello World example that shows you how to train and build a LensKit recommender. LensKit is an open source toolkit for building, researching, and studying recommender systems. Its goals are to support building recommender systems. We want it to be usable to build working real-world recommender systems. Particularly, we're focused on small to medium scale deployments. I'll talk a little bit later about how our organization is such that our APIs should be usable in situations that need to scale farther. We want it to be useful as a platform for research in recommender systems. We want it to be useful for performing algorithmic research, research and evaluation techniques that use existing algorithms, as well as user experience research and other research that needs a recommender but isn't about building the recommender itself. We want you to be able to take LensKit, use it as a recommender in those kinds of research projects. We also intend it to be useful as a tool for education about recommender systems. A useful tool for studying how recommender systems work, how to implement them, and provide good implementations to use in that context. The core APIs that LensKit provides start with the recommender interface. And this doesn't do much on its own, but it provides access to the rest of the APIs, such as the rating predictor, which is an interface for predicting user ratings for items. You give it a user and an item, or a bunch of items, and it gives you back the predicted rating for those items to support the predict task in recommender system. The ItemScorer is a lot like the rating predictor. It generates a user-personalized score for an item. A lot of times this will be a predicted rating, but it might be something else, such as just a similarity score or a relevance score of the item for the user's preferences and profile. And then finally, the ItemRecommender recommends items for users. You give it a user ID and the number of items you want recommended, and it will give you a list of recommendations for that user. LensKit's code is divided into several modules. First, there's the LensKit API module, and it primarily provides the interfaces that I just talked about. It is intended to be the public-facing API for building applications that use LensKit to provide the recommendation. This API is decoupled from most of the rest of LensKit, so you can use LensKit's recommend and predict APIs without using the LensKit implementations. And this is to allow you to replace the implementation easily. You can use LensKit completely to build your application and prototype it and roll it up through as many users as it can scale to. And then when your user base grows beyond the scaling capabilities of LensKit's algorithm implementations, you can use a shim that implements the LensKit recommend APIs on top of, say, Apache Mahout, or your own infrastructure built on Hadoop or whatever clustering mechanism you're using, and scale out your recommender capabilities with minimal changes to your front-end client code. The LensKit Data Structures module provides data structures used by LensKit and its APIs. This is the only other LensKit module that LensKit API depends on, and I'll talk in a little bit about what the data structures it provides are. LensKit Core provides the foundational utilities and infrastructure for the rest of LensKit. It provides the capacity to configure LensKit recommender algorithms, to handle model serialization, various things like that that you have to take care of when you're actually deploying a recommender in a web application. And it also provides utility classes that are used by the rest of LensKit, and it's where our data access layer lives. The LensKit eval module provides LensKit's evaluation toolkit. We'll talk more about that in another video. And then the LensKit KNN, SVD, Slope 1 modules provide implementations of different families of recommender algorithms. KNN provides user-user and item-item collaborative filters. SVD provides a matrix factorization collaborative filter. And then Slope 1 provides an implementation of another recommender algorithm called Slope 1. LensKit also uses a library called FastUtil. Now, Java generics interact badly with primitives. If you've got a list and you want to store a bunch of longs in it, that doesn't work very well memory-wise or efficiency-wise. FastUtil provides primitive versions of Java collections. For example, it provides a long list interface, which implements list of long, but allows you to access the numbers in the list without incurring the overhead of boxing or allocating an object that wraps the primitive long. LensKit uses collections from FastUtil extensively for performance. You'll see in the LensKit source code, you'll see many long lists, long to double maps, and things like that. The LensKit Data Structures module builds on FastUtil and provides some additional data structures that we use in LensKit. First is the sparse vector. This is a map of long IDs, user or item IDs. LensKit assumes that every user and item in the system has a unique 64-bit numeric ID represented as a long. And this provides a sparse vector that we can do linear algebra operations on. A cursor is basically an iterator with a close method, and this is used to encapsulate access to files, database connections, and other data sources where you need to be able to close the underlying resource. It also provides scored ID, which associates a long ID, such as a user or an item ID, with a score. It provides some additional collection utilities as well as symbols, which if you've used a language like Lisp or Ruby, you've seen symbols which are intern strings that allow very fast comparisons. We use these in a few places in LensKit. Sparse vector merits a little bit more discussion. It's a sparse ordered map from long keys to double values, and it's sorted by key. The valid keys are fixed when the vector is created. So you create a mutable, you create a sparse vector, and you give it the set of keys that are going to be valid for that vector. And after you've done that, you cannot add any more keys or remove keys. However, certain keys may be set or unset. So you don't have to use all of the keys. It allocates storage for all of them. And this allows the vector to be implemented very quickly using binary search. Sparse vector is the top level of a triad of classes here that provides it's an abstract class that provides a read-only interface to the vector. So if you have a sparse vector, you can read it using a get method. I'll show you its API in just a little bit. There are also mutable and immutable implementations of sparse vector called mutable sparse vector and immutable sparse vector, respectively. And a mutable sparse vector does just what it says. It can be modified. You can set values. You can unset values. You can scale it. You can add to it, etc. An immutable sparse vector cannot be modified. So we have sparse vector, and then it's abstract. Then we have two concrete subclasses of it, mutable and that extends sparse vector, and immutable sparse vector. So if code has a sparse vector it can read it using methods such as get, which gets you the value for a key, but it cannot modify it. It's not, however, guaranteed that nobody else has a reference to that sparse vector that they can modify, and so it's not really thread safe. Mutable sparse vector lets you modify the sparse vector and is decidedly not thread safe. Immutable sparse vector cannot be modified. So if you have an immutable sparse vector, not only, if one component has an immutable sparse vector, not only can that component not modify the vector, it is guaranteed that no other component is simultaneously modifying the vector. So it can be remembered, it can be used concurrently by multiple threads, etc. And there are methods to convert between these. A method to make any vector immutable. If it's a mutable sparse vector, it copies it and gives you an immutable copy. If it's immutable, it just returns the immutable vector because you can reuse it. And then a method that goes the other way that gives you a mutable copy of whatever vector you have. If it's already mutable, it makes a copy. If it's immutable, it makes a copy, and the result is a mutable sparse vector that you're free to implement. Sparse vectors also support linear algebra operations. Mutable vectors support adding in vectors or adding a constant value to every entry, subtracting, multiplying, either multiplying by a scalar or doing pairwise multiplication by the elements in another vector. These modify the vector in place. So a common pattern is to create a mutable sparse vector that has keys you need, then start performing algebra operations or arithmetic operations that accumulate the results into the sparse vector. Then oftentimes you'll convert that to an immutable sparse vector to store. There are additional operations such as dot products, etc. And let's look briefly at the Java doc for the sparse vector class. So this is the documentation for sparse vector, the root abstract class. And it provides a bunch of methods. I'll talk about a few. Contains key is like contains key for a map. It sees whether that key is in the vector and is set. There is a get method that gets the value for a key. Unlike Java map, get throws an exception, illegal argument exception, if the key is not in the vector. There's another version of get that takes a default and returns that default value if the key is not in the vector. There are also methods to iterate over a sparse vector, and you get vector entries which have the key and the value. It supports a variety of other methods, not all of which I'll get into right now. But it has methods like the dot that computes the dot product between this and another vector. You can also get the L2 norm or Euclidean length of the vector, the sum of the vector, and the average value of the vector. Immutable sparse vector does not add any additional methods. It just guarantees that the sparse vector cannot be changed. Mutable sparse vector adds methods to modify the sparse vector in place, and you can look at the Java doc for more details on what those methods are. The ItemRecommender API has three primary methods. First, there's just a recommend method that takes a user ID and uses whatever defaults the recommender chooses to provide you with some recommendations. The last method takes the user ID, the number of recommendations to generate, and additional candidate and exclude sets. And if either of these sets are null, the ItemRecommender will use some defaults. Typically, the candidate set will be all items, and the exclude set will be the items the user has rated. And the recommender is supposed to return n or up to n recommendations from the candidate set that are not in the exclude set. And this allows the client application to have a lot of control over what items might be recommended. The ItemScorer has also three methods. The first one is very simple. You give it a long user ID, a long item ID, and it gives you back a score. The second, you give it a collection of items, and it gives you back a sparse vector that maps the items to the scores. And if it could not generate a score from one of the items, that item is omitted from the vector. And the third takes a user ID and a mutable sparse vector. And it takes the mutable sparse vector's set of valid keys, which is called the key domain. It doesn't care whether the key is actually set or not. It just uses the set of all valid keys. And it tries to score all of them and sets the scores in the sparse vector. Most scorers leave unset, most scorers unset any item for which they cannot generate a score. There's an abstract base class, abstract ItemScorer, that implements the first two methods in terms of the third. So you just have to implement a method that accumulates scores into a mutable sparse vector if you're going to implement an ItemScorer. Now I'll talk just a little bit about data access in LensKit before we talk about how an algorithm is structured. The primary data type in LensKit is an event, which is some user interacting with an item, and it may have a timestamp. Rating is one subclass of event that is a user rating an item with a particular value, or a user unrating an item. Event data comes from data access objects, or DAOs. The master one of these is Event DAO, that just provides access to the events known to the data source. There's other interfaces that provide more nuanced access, such as User Event DAO allows a component to get the events for a user, and Item Event DAO allows them to get the events for a particular item. So we'll look just a minute at these interfaces. So Event DAO has three methods. One is stream events, and that gets all events in the database that is backing this DAO, which might be just a list of events in memory. It could be a database accessed with JDBC, MongoDB, or CSV file, and it just gets all the events in the database. Then there's two versions of that, or a version of that filters. You can get all the events of a particular type. So LensKit organizes events by their class. So you can say stream events rating.class, and it will give you all the ratings. And then the third allows you to access the events in a particular order, such as timestamp or user ID. And these methods all return cursors. So you have to close the cursor when you're done with it, using a try finally, or if you're using Java 7 or later, you can use a try with resources block. And it's a recurring pattern in LensKit that if a DAO method returns a cursor, its name is stream. So if you have a method that gets, say, the events for a user, this is the user event DAO. It can get the events for a particular user, filter them by type. It just returns an object. You're not going to have to close it. A stream method, such as the ones in Event DAO, or this, which streams all the users in the system, it returns a cursor that the code that's calling the DAO is responsible to close. So to use LensKit, now that I've covered some of the pieces, you first have to create a LensKit configuration. You then create or configure your data access object or objects. After that's done, you configure the algorithm you want to use and its parameters. You build a recommender from this configuration, and then get individual recommender components from the recommender. And I'll show some example code that does this in a little bit. But there's this thing you have to do of configuring the algorithm you want to use. And to understand how that works, we first need to talk about the structure of a LensKit algorithm. LensKit algorithm implementation, or any given LensKit algorithm implementation, usually implements the ItemScorer interface. We provide default generic implementations of rating predictor, which just takes an ItemScorer and makes sure the scores are within the range of valid ratings, and an ItemRecommender that just returns the top n items by score. So many recommenders just need to provide an ItemScorer to do the interesting work. That ItemScorer itself may depend on many components to do its work, The goal of this is to allow our algorithm implementations to be reconfigurable and reusable. Both have their individual pieces reusable and have the structure reusable with swapping out individual pieces. We organize all of these components with a technique called dependency injection. Dependency injection is just a design pattern for organizing classes that use each other. The basic idea is that when one class needs another class to do its job, rather than constructing that class itself, it requires an instance of that class to be provided via a constructor, parameter, or a setter. We call this injecting the dependency, injecting the class that it needs. And then a dependency injector just automates the process of instantiating many classes built using this design pattern. If you've worked with Juice or Pico Container or Spring or on the .NET platform Ninject, then you've worked with a dependency injector. In LensKit, we use a dependency injector called Graft, which is very much like Juice but provides some additional capabilities that we need. For an example of this, let's look at the constructor for the TopNRecommender, or ItemRecommender. TopNRecommender is the default implementation of the ItemRecommender interface. If you don't specify an ItemRecommender in LensKit and you properly configure an ItemScorer, then it will give you a top-n ItemRecommender that just picks the top n items, 5, 10, whatever, by the scores provided by the ItemScorer. And its constructor is first annotated with the Java annotation @inject. And this tells Graft to use this constructor when instantiating a top-n ItemRecommender. This constructor then has 3 constructor parameters. The user event DAO, so it can get the events for a user. The item DAO, which lets it get a list of all valid items. And then the ItemScorer that it's going to use to score items in order to produce the recommendations. And then LensKit will use Graft to go see what ItemScorer you've configured. It will look at its dependencies, if it has any. We call each of these constructor parameters in the @inject constructor a dependency. And it will instantiate the whole graph of objects automatically. So common components in a recommender algorithm, first is the ItemScorer, which is usually where the interesting logic lives for most recommender algorithms. If an algorithm has particular needs in the rating prediction side or the ItemRecommender side, it can provide additional implementations of those. And then sometimes it'll use a baseline score and a couple of roles. One, to do data normalization before doing a more sophisticated piece of the algorithm. Or another, sometimes to use a baseline such as the user's average rating or the global average rating, which can always be used as a fallback in case the primary interesting recommender logic can't compute a score for a particular item. There can also be normalizers that do data normalization to sanitize the data and clean it up for the algorithm. So, as an example, this configuration sets up a recommender that just uses the user item personalized mean. And this is computing, it takes the mean rating for each item, and then it computes the average offset of the user's rating from each item's mean. So if the user rates one item half a star above average for that item, that's 1/2, and it averages those offsets. So we get this personalized average for the user, and this configures such a recommender. Let's look at a diagram of the objects that this configuration produces. So at the top we have this root, which just serves to collect dependencies on all the components we use. The rating predictor and the ItemRecommender are both provided by these providers. And a provider, it's an interface, it just has one method, get. And it's used to allow for some decoupling between constructions, some more sophisticated instantiation patterns. And And when you look at a diagram of a LensKit configuration, this kind of an arrow here means that one component, one class provides another. The provider in turn depends on the event DAO and the user event DAO and the item DAO. It gets these from, we can follow the dependency arrows, a prefetching user event DAO, which is the default implementation of user event DAO. A prefetching item DAO, which is again the default implementation. Most of these relationships come in through default implementations. This kind of an arrow means that one class depends on another. They in turn use the event DAO, which has this provider just from the code that draws these diagrams. But the ItemScorer is the one we configured, the user mean ItemScorer. And it's dependent on by the root, but the simple rating predictor provider depends on the user ItemScorer. You can follow that arrow, as does the TopNRecommender. And this is the user mean ItemScorer that we configured. And the user mean ItemScorer actually uses user mean offsets from some other scores, and it depends on a score with the qualifier, this thing that has an @ We'll look at that in a little more detail in just a little bit. And it depends on the item mean rating ItemScorer, which scores items just using the item mean rating. So this configures this ItemScorer that basically has two stages. It uses the item mean rating, and then it computes user offsets from that in order to do the final scores. The user mean item rating score is built by a builder, and that builder in turn depends on the event DAO. So the configuration that generated this takes the form of what are called bindings. And a binding says what implementation to use for a particular class. So the first binding we see here says that we should use myDAO, an instance of event DAO, as the implementation of the event DAO class. The second binds ItemScorer to user mean ItemScorer, and that means we should use the class user mean ItemScorer as the implementation for the ItemScorer interface. Java generics are used to enforce at compile time that the class you're binding to actually implements the interface you're trying to bind to help you avoid mistakes. The second line uses what's called a qualifier. The first class mentioned there is a qualifier, which is an annotation class to say that this ItemScorer is in a particular role. It's the baseline for the user mean. We'll see in just a minute how that's specified, but we're saying that use the item mean rating ItemScorer as the baseline for the user mean ItemScorer. So let's look at that a moment. So the user mean ItemScorer constructor has @inject to say that it expresses dependencies, and it's how you actually build one of these. It requires the user event DAO. It also uses another ItemScorer, and it's annotated with user mean baseline. And that tells LensKit, look for a qualified binding, a binding that specifies we really want the user mean baseline for the ItemScorer. And this is used to allow us to express what role the ItemScorer is going to play if it's not just an ItemScorer that we want to use normally. And then it also takes a user history summarizer and a damping term. So the item mean rating ItemScorer, it has this default provider annotation, and that means that if something needs if we need an item mean rating ItemScorer, build one by instantiating this provider class called item mean rating ItemScorer.builder and call its get method. And we just use these to separate it out so our constructors are lightweight and don't have to do a lot of work. The builder then has an injectable constructor that takes an event DAO and then a damping term. And the event DAO is annotated itself with transient. And what transient means is that the builder is making a promise to LensKit. And it is promising that, okay, it needs the event DAO to build the item mean rating item scorer. But once the item mean rating item scorer is built, that object is free of the event DAO. It's not needed. This is used to provide some advanced features in LensKit for automatically reconnecting recommenders in web applications. But it's a common pattern in LensKit if a class needs complex computations to build it, then we'll often have a builder implement those computations so the constructors themselves remain simple. And if all of this seems fairly complicated, don't worry too much. There are a lot of moving parts, but after you've built a recommender or two, it will hopefully all come together fairly simply, and we provide many examples of how to configure recommenders to do what you want. So let's put this all together and look for a minute at the LensKit Hello program, which configures and builds a simple recommender and outputs some basic recommenders from it. So it's going to read input from ratings.dat, which is some tab-separated ratings, and it's going to recommend for some users. And we just parse the command line arguments. That's kind of boring. I'll let you read that in your own. The LensKit Hello project is available from the Group Lens Bitbucket if you want to check it out yourself. The interesting logic is in the run method. So the first thing we do is we create a simple file rating DAO that's going to read the data from the input file with our delimiter. And this simple file rating DAO implements the event DAO interface. We then, because reading repeatedly from a CSV file can be kind of slow, and the file's probably not terribly big, we create an event collection DAO that has just a list. We pre-read all the data from the CSV file or TSV file into a list and use that list to make an event collection DAO. And that's going to be the real data source that our recommender operates from. We then create a LensKit configuration. And the LensKit configuration class is what you use to configure LensKit recommenders. And we bind event DAO to our DAO implementation to use that as for the data access. We then configure the ItemScorer. And in LensKit Hello, we configure a basic item-item collaborative filter. So we configure the item-item scorer as the ItemScorer. We then configure a baseline score, and this is another one of those qualifiers that defines a role, and it says this isn't the main item score, this is the baseline one, and baseline fills two roles: one used for data normalization, two used to provide a fallback in case the collaborative filter can't do a score. And we're going to use the user mean item scorer. We're going to give it a baseline of item mean, so that the baseline in this configuration is the configuration we just looked at as a complete LensKit recommender. We then configure a user vector normalizer. We then build the recommender using LensKit recommender.build static method, and that gives us a recommender, and it throws an exception if there's some error while building it. Then we get the item recommender from that, and the recommender interface is capable of dealing with configurations that maybe can't do item recommendation or can't do rating prediction, and it will return null in that case. And we designed it this way so that if you have an item recommender, you know the configuration can do item recommendation, or at least it claims it can. But so in this case, we configured, there should be an item recommender. We configured the relevant pieces, so we just have an assert there. And then for the user specified in the command line, we get 10 recommendations for each one, and we print them out as output. For more information on how to use LensKit and the details of these various classes and components I've talked about, the APIs and components for LensKit are documented in our Java doc. On the Bitbucket wiki, we have long-form documentation about the anatomy of a recommender, about the components of particular implement algorithms. Also, we have a mailing list that we encourage you to ask questions on. All of this is available from our website at lenskit.grouplens.org. We hope that you enjoy using LensKit, and please let us know the cool things that you're making with it.